G'day guys. Today's lecture, the 2-hour lecture, the two chapters that we're going to cover in the workbook today, chapters 33 and 34, they're actually all about orthogonal diagonalization. This first lecture, the first hour, we're just going to look at, what is orthogonal diagonalization. Now that we've already looked at, or had a close look at eigenvectors and eigenvalues, and seen what we mean by diagonalization now and what it means to diagonalize a square matrix, we're going to look at a special case of so-called orthogonal diagonalization. And in doing so, we're going to start looking at some special classes of matrices that characterize this notion of orthogonal diagonalization. The next chapter, chapter 34, we're going to see an application of this to quadratic forms, and in particular classifying conic sections, which I think you would have studied some conic sections if you've done the Math 1052 course. So we'll look at that in a little bit more detail. But now that we know about diagonalization, and in particular once we finish this chapter on orthogonal diagonalization, we'll know something even more and be able to deal with the most general type of conic section we can have, right? And it'll even allow us to graph such curves in the xy plane. All right, it's a nice little application of linear algebra. Okay, so firstly, I guess, what are orthogonal matrices? Well, this is what we're going to be looking at, given an n by n matrix A. So we know what it means to diagonalize a matrix A, but we call A orthogonally diagonalizable if there exists an orthogonal matrix P such that P inverse equals its own transpose. So that's the key identification with this equation. So that is that P inverse equals its own transpose. And in fact, this is the definition and the one property that characterizes what we mean by an orthogonal matrix. All right, so we've seen, remember to say that a matrix A, a square matrix A, is diagonalizable just means that this product, that means there exists an invertible matrix P such that P inverse AP is a diagonal matrix. But now what we're doing is just adding some additional information onto that about this matrix P, and that is that it's orthogonal. And the definition of that is that the inverse of that matrix is equal to its own transpose. Okay, so actually orthogonal matrices are very easy to invert. Okay, so I guess there's another way of looking at, or another way of defining an orthogonal matrix. We can define it as a real square matrix. So when I say a matrix is real, I mean all of its entries are real numbers, okay? So not complex numbers. So an orthogonal matrix is a real square matrix, let's say Q, such that the columns of the matrix Q are mutually orthogonal unit vectors. Okay, so all that means is if we take two distinct columns of that matrix, so if I call the columns VI, so first column V1, second column V2, and so on, and that just means the dot product of any two distinct columns is 0. And what's more, so that's the meaning of the word orthogonal. And what's more, they're unit vectors. So if I take the dot product of one column with itself, I get 1. All right, so just remember that when we write the magnitude of the vector VI, this is just the square root of the dot product of that vector with itself. All right. Okay, so that's the key property, I guess, or the way we can construct orthogonal matrices is by taking a set of mutually orthogonal unit vectors and placing them into the columns of that matrix. If we do that, by virtue of matrix multiplication, All right, so if I take the transpose of that matrix, that means the rows of the transpose are mutually orthogonal unit vectors. Right, so it means when I multiply Q by its own transpose, we can then invoke that property of the columns of Q, that they're mutually orthogonal unit vectors. So when I take the dot product of any two vectors, so when I multiply out the matrix with its transpose, I'll either get 1 or 0, okay, and that'll give me the identity. So in particular, that's a consequence of constructing the orthogonal matrix in this way by taking the set of mutually orthogonal unit vectors, placing them into the columns, and then we immediately have that Q times Q transpose equals the identity. All right, and so that's a consequence of the construction of the orthogonal matrix as I've described above. All right, so one property, or a further consequence, I should say, is that the determinant of an orthogonal matrix is only ever plus or minus 1. And so we can see that if we have an orthogonal matrix, if we have an orthogonal matrix Q, so that implies that Q times Q transpose is the identity matrix. Okay, it doesn't matter which order you take that product. You could either write Q by Q transpose or Q transpose Q. But now if I take the determinant of both sides of this equation, so that's the determinant of Q times Q transpose will equal the determinant of the identity matrix. On the left-hand side, I've got the determinant of a product. All right, so this is just the determinant of Q multiplied by the determinant of Q transpose. And on the right-hand side, the determinant of the identity, so that's just equal to 1. Right? The identity is just the square matrix with 1s on the diagonals and 0s everywhere else, so its determinant will just be the product of the entries on the diagonal. And there's a further property of determinants, that the determinant of the transpose of a matrix is equal to the determinant of that matrix. So we end up with that the determinant of Q all squared must equal 1. All right, so the only possibility of the determinant for an orthogonal matrix is that it can be plus or minus 1. Now, we'll look at this in the next lecture in chapter 34, but I'll just make a comment on the side. So as an aside, in 2 dimensions, so I'll say in R2, an orthogonal matrix with determinant equal to 1 is equivalent to a rotation. And an orthogonal matrix with a determinant equal to -1 is equivalent to a reflection. So 2 types of linear transformations are characterized by the orthogonal matrices in 2 dimensions. So the 2 by 2 matrices, they're either going to be rotations or reflections. They'll correspond to those linear transformations. That's not the case in R3, it turns out. You can get some orthogonal matrices which are neither rotations nor reflections, but a combination of the 2. Okay, and things can be a little bit more complicated in higher dimensions, but in 2 dimensions this is certainly the case, and we'll make use of this later on in the lecture that follows. Okay, so I mean, this is just demonstrating some simple properties of orthogonal matrices. What we're actually going to find is that there's an intimate relationship between these orthogonal matrices and the so-called symmetric matrices, which we can now define. And it turns out this has all got to do with orthogonal diagonalization. So diagonalization with an orthogonal matrix P. All right, so just to define what we mean by a symmetric matrix, and these are very straightforward to identify, we say that a matrix is symmetric if and only if it's equal to its own transpose. Okay, so you can see why we call these symmetric matrices. I mean, have a look at this, this 3 by 3 matrix. There's a sort of symmetry about the diagonal, all right, about the main diagonal here, with entries -3, -2, and -3. So in particular, if I interchange the rows and columns, I get exactly the same matrix. So the entries in row I are all equal to the entries in column I. All right. So when I take the transpose of this matrix, so if row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3, well, I get back exactly the same matrix that I started with. Okay, so that's the property of a symmetric matrix. Very, very easy to identify. All right, if you can, especially if you've got it written out, hopefully you can look at that 3 by 3 matrix and see immediately that symmetry about the main diagonal. Okay, that these corresponding entries are the same. All right, these ones, and the zeros. All right, so that's the main property of the symmetric matrix. There's one thing, or one result we can prove to do with eigenvectors of a real symmetric matrix. So I'll just remind you again. So this result is only for real symmetric. And when I say real, I mean that the matrix has real entries. Okay, I think I said that before, but that's all it's referring to. Okay, so the result that we'll prove, I mean, the proof is not hard, but I guess a little bit enlightening and just gives you a way of thinking about orthogonality and the dot product. It gives you a new way of thinking about it, I guess. That if A is a real symmetric matrix, then the eigenvectors corresponding to different eigenvalues are orthogonal. Now, there was a result we saw yesterday that for any matrix, eigenvectors corresponding to distinct eigenvalues are linearly independent. But this is saying something a bit stronger. Right? It's saying, well, in the case that the matrix is real symmetric, they're not only linearly independent, but they're orthogonal. Okay, so just some notation I'll use in this proof. I'll just demonstrate by example in 3 dimensions. So when we take the dot product of 2 vectors, right, if I write them out as column vectors with entries v1, v2 and v3, and I take the dot product with the vector w with entries w1, w2 and w3, we know how to take the dot product. We know how that's defined. We just take the product of the corresponding components and add them together. So that's v1 w1 plus v2 w2 plus v3 w3. Okay, but I just also want to point out that if I take the transpose of V and write this just using regular matrix multiplication, if I write that matrix product, okay, so V transpose now, if I'm thinking of V and W as column vectors, V transpose is then going to be a row vector, okay, with 1 row and 3 columns. All right, and so this product, thinking of that as a matrix product, that's going to just look like V1, the row vector V1, V2 and V3, multiplying the column vector W1, W2 and W3. All right, and you can see when I just multiply that out just using regular matrix multiplication, that's going to be precisely the dot product. Okay, it's going to just give the sum of these terms, which is precisely how we've defined the dot product. So I'll use this notation in the calculation, and what we'll consider is the case where we've got a real symmetric matrix and we've got two eigenvectors, v1 and v2, corresponding to distinct eigenvalues. All right, where lambda 1 is not equal to lambda 2. Oh, there's another property of matrices I just want to remind you of. I guess I'll say remind you of. You may have seen this before, but for any size matrices, including row vectors and column vectors, if I take the transpose of a product of matrices, this will give me the product of the transposes of the individual matrices, but in the reverse order. So that'll be equal to B transpose A transpose. All right, I won't prove that, just state that result. You might have seen that in Math 1051. I'm not sure. But we'll use this property of the transpose anyway. All right, so we've got two eigenvectors corresponding to distinct eigenvalues. Now let's see what we can deduce. We want to show, all right, the result is that it says that these eigenvectors must be orthogonal. So I want to show that their dot product is equal to 0. Or equivalently, as I've introduced this notation using the transpose, equivalently I just want to show that V1 transpose V2 equals 0. Alright, so to do this we'll start by considering that product, V1 transpose V2. And in fact I'll multiply that by one of the eigenvalues, lambda 1. Alright, so because we know that lambda 1 V1 is just the matrix A times V1, and I can consider the lambda 1 to be inside, I can write it like this, lambda 1 V1 all transpose. That's just scalar multiplication there. That's not going to affect the transpose at all. But now what I can do is use the fact that V1 and lambda 1 are an eigenvector-eigenvalue pair and write that as A times V1 all transpose, and then invoke that property of the product of the the transpose of the product is the product of the transposes in the reverse order. V1 transpose A transpose V2. Okay, but remember we're dealing with a symmetric matrix here. So A is a symmetric matrix, so that means it's equal to its own transpose. So I can just replace A transpose with A, and I'll just say, since A equals A transpose. And we also know that V2 is an eigenvector of A. Okay, so we've got A standing next to V2 on the left, so it means I can replace this with lambda 2 V2. And this is just scalar multiplication, so that's just lambda 2 multiplied by V1 transpose V2. Okay, so what have we shown then? We've shown that lambda 1 multiplied by that V1 transpose V2 is equal to lambda 2 times that same product of row vector by a column vector. Okay, so I can actually rewrite this equation. I can just move the term involving lambda 2 over to the left-hand side, for example, and write it as lambda 1 minus lambda 2 multiplied by V1 transpose V2 equals 0. All right, so I've got some product of two numbers equal to 0. So since we've specified, we've stated at the outset that lambda 1 and lambda 2 are two distinct eigenvalues, it means this difference, lambda 1 minus lambda 2, is not 0. Right? So we can actually divide through by that factor because it's not 0. So since lambda 1 is not equal to lambda 2, that implies the only other possibility is that the one remaining factor must be equal to 0. So V1 transpose V2 is equal to 0, which is the result we are after. Okay, so we've just shown from that simple calculation that if we've got a real symmetric matrix, that the eigenvectors corresponding to different eigenvalues are orthogonal. Now, what have we just finished saying about orthogonal matrices? Well, these are the matrices that we can form by taking a set of mutually orthogonal unit vectors and placing them into the columns of that matrix. All right. Now, what we've just seen from this calculation is that in the case a matrix A is real symmetric, the eigenvectors corresponding to different eigenvalues are orthogonal. So we can actually bring these results together, and in fact, this is one of the main results of the lecture that's on this page, is that we end up with, the proof, the careful proof of this result is actually a bit complicated, but we can start putting the pieces together at least. And this result we've just seen, plus what we'll look at now, is starting to put the pieces together. So in fact, it's straightforward to show that if a matrix is orthogonally diagonalizable under that assumption, it's very easy to show that the matrix is symmetric. So remember how we've defined an orthogonally diagonalizable matrix. So that means there exists, okay, so the backward E, right, there exists a matrix P such that P inverse is equal to P transpose, and this P transpose, this product P transpose AP is equal to a diagonal matrix D. All right, and this is kind of what we looked at yesterday. In the case, it was just P inverse AP is a diagonal matrix. We understand now how to construct P, and we know exactly what entries are on that diagonal, or exactly what entries are in that diagonal matrix, namely the eigenvalues of A. Okay. Another way, I'll just remind you, another way of writing that expression is to isolate A, and this is a characterization for the matrix A, is that it can be written as a product P times D times P transpose. All right. All right, so in that case, we can actually use this, and we want to show that assuming the matrix is orthogonally diagonalizable, so in other words, assuming that A factorizes into this product P times D times P transpose, then what can we deduce about A transpose? Well, let's substitute this in. P, D, P transpose, all transpose, and use the property of the transpose, okay, this transpose operation which just replaces columns with rows, so first column becomes first row, second column becomes second row, and so on. But there's that property of the transpose that this then is this expression I've written here is just the product of the individual transposes in the reverse order. So that will be P transpose, all transpose, multiplied by D transpose, multiplied by P transpose. Now this first matrix, right, if I take the transpose twice, that just takes me back to where I started, right? So that's the matrix P. So this is using the property of transposes. That I mentioned over here. All right, so P transpose, or if I take the transpose twice, I just end up right back where I've started. D is a diagonal matrix. Okay, so it's the only non-zero entries are on the diagonal. So taking the transpose is not going to affect that at all. And well, there's nothing I can do with P transpose. But the point is now I've got this product P times D times P transpose, which is exactly A. All right, so what we've just shown is that if a matrix is orthogonally diagonalizable, then it is symmetric. This is actually logically equivalent to the following statement: if A is not symmetric, then it is not orthogonally diagonalizable. All right, this logical equivalence is known as, especially if you've studied Math 1061, you will have heard of the contrapositive of a statement. If you have A implies B, that's logically equivalent to not B implies not A, or the negation of B implies the negation of A, which is exactly what I've just stated here in the context of this result. Okay, that's actually the origin of that language when we say if and only if, A if and only if B. So it's to do with this contrapositive, this logical equivalence. Anyway, that's just a little aside there. So that wasn't too difficult to show that result, but actually it turns out that the converse is also true, namely that if a matrix is symmetric, then it is orthogonally diagonalizable. Right? We're not going to prove this, but that's the result of this if and only if statement that I've made, that I've put in the box here, which is really one of the main results of this lecture, and that is that an n by n real matrix is orthogonally diagonalizable if and only if it is symmetric. Now that's an incredibly powerful result, right? Because it completely characterizes the matrices which are orthogonally diagonalizable. All of the matrices which are orthogonally diagonalizable are the ones which are symmetric, and there are no others. Okay? So, the proof is a little bit complicated. In fact, I guess it's summarized a little bit down here at the bottom of page 212, especially in part 2, this statement number 2, relating to the eigenvectors and eigenvalues of a symmetric matrix A, or a real symmetric matrix A. So there are two results. One is that all the eigenvalues of A are real numbers. In fact, we're not going to prove this now, but we're going to prove this in tomorrow's lecture. And I'll just mention that the proof requires complex matrices. The proof requires complex matrices, which we'll look at in chapter 36, right, the very last chapter. All right, we'll actually make the proof for a much more general class of complex matrices, which includes the real symmetric matrices. So we get that result for free once we look at the result of chapter 36. And this part 2 is really where the result in the box comes from, is that A has n linearly independent eigenvectors. Remember, that's the result that says that we can diagonalize a matrix. Right? If we've got an n by n matrix, can we diagonalize it? Well, the answer is yes, if we have n linearly independent eigenvectors. That's what we saw yesterday. All right? And the proof of this result in part 2 requires an algorithm known as the Gram-Schmidt process, or the Gram-Schmidt algorithm, and also makes use of induction, which I introduced in yesterday's lecture. The Gram-Schmidt process is just it's a constructive process that turns a set of linearly independent vectors into a set of orthogonal vectors. all right, which you can then, once you get a set of orthogonal vectors, you can work out their lengths and turn them into unit vectors just by dividing each one by their own length. So it's this constructive algorithm that, given a set of linearly independent vectors, you can construct orthogonal ones. And yeah, it builds on this result from page 211 as well, and other results from linear algebra. So I didn't really want to go into that too much, but suffice it is to say that the result in this box is one of the main take-home messages from the lecture today. Okay, these symmetric matrices completely characterise the orthogonally diagonalisable matrices. So in other words, we get an answer. Can we always, well, if a matrix is symmetric, remember that this is one of the problems or one of the questions that I introduced yesterday. Can we diagonalise a given matrix? Right? Well, the answer we came up with was yes, only if we have enough linearly independent eigenvectors. But now we know from this result is that if it's a symmetric matrix, we can always diagonalise, right? And we can do so with an orthogonal matrix. All right, here's an example, just to see what these look like. We can work through an example. In fact, this is the 3x3 matrix that has been travelling with us for the last couple of lectures, this 3x3 matrix. We've already worked out all of its eigenvalues and the corresponding eigenvectors. We've seen that it has 3 distinct eigenvalues, and we've also seen what the eigenvectors are explicitly. But now I also make this observation, is that the matrix we've been dealing with is in fact symmetric, right? It's a symmetric matrix. I mean, this is what I pointed out on page 210. The example at the bottom of page 210 was exactly that matrix. Clearly, it's symmetric. All right, so this is the matrix we've just worked out all of its eigenvalues and eigenvectors in the lecture yesterday. So one thing we'll note about this matrix is all of these eigenvectors, I mean, we can, because there are only 3 of them, it's not too difficult to check this exhaustively, that the dot product of any 2 distinct eigenvectors, so that's with I not equal to j, is equal to 0. Okay, the dot product of those two vectors with I not equal to j is always equal to 0. And in fact, we know this even without checking the dot products explicitly. We know this from the result on page, 211. That if a matrix A is real symmetric, then the eigenvectors corresponding to different eigenvalues are orthogonal. Well, this is a symmetric matrix. All right, what we've got is a symmetric matrix. We've only got different eigenvalues, so it means all the eigenvectors corresponding to those must be orthogonal. So we know that immediately from the result on page 211. All right, I mean, you can check it straight away. If I take the dot product of V1 with V2, you'll get 1 plus 0 plus negative 1, which is 0. So you can work it out explicitly, but we already know it from that result on page 211. Another thing we can do is work out the magnitudes of each of the vectors. So for V1, it's just going to be the sum of the, well, for each of them, it's going to be the sum of the square of the components. So in this case, the magnitude of V1 is the square root of 2. The magnitude of V2 is just 1 plus 4 plus 1, so that's, well, root 6. And the magnitude of V3 is just root 3. Okay, so what we can do now is normalize the eigenvectors. They're already orthogonal, in fact, but in other words, now all we have to do is turn them into unit vectors. turn them into unit vectors. So we'll do that just by, I'll call it vi hat, just by taking the vector vi and then dividing by its own magnitude. All right, so what do these look like now? So that implies, so v1 hat is just going to be 1 on root 2, 0, and negative 1 on root 2. v2 hat is just going to be 1 on root 6, 2 on root 6, and 1 on root 6. And v3 hat will just be 1 on root 3, negative 1 on root 3, and 1 on root 3. Okay, so now we've got our set of mutually orthogonal unit vectors of the matrix A at the top of the screen. Okay, so what I'm trying to do now is orthogonally diagonalize this matrix. Okay, so we've worked out the mutually orthogonal unit vectors. So now what I can do then with those vectors is to place them into the columns of a matrix P, okay, which must then be an orthogonal matrix. All right, so I'll just observe that this set of vectors, these form an orthonormal set, meaning they're orthogonal and they're unit vectors, or they're mutually orthogonal and they're unit vectors. So we now form up this matrix P, where I place these mutually orthogonal unit vectors into the columns of P. And remember, all we've done is just taken eigenvectors and divided through by their own magnitude. So they're still eigenvectors. All right? These are still eigenvectors of the matrix A. Okay, so we just place these into the columns of a 3 by 3 matrix. V2 in the second column, and V3 in the third. And I'll just make a comment. This is just V1 hat, V2 hat, V3 hat in each of the columns. And this, I'll say which orthogonally diagonalizes the matrix A. All right, so, I mean, you should just check that this matrix P, its transpose, equals its inverse. All right, so check that it genuinely is an orthogonal matrix. But you should be able to, I mean, you should be able to see that just by using the fact that these columns are orthogonal. Okay, and so when you take the transpose and multiply the matrices together, matrix multiplication just says when you multiply one row of the matrix on the left with a column of the matrix on the right, that's just going to be the dot product of any two of these eigenvectors, all right, which is either going to be 1 or 0. Okay, and I mean the fact that these columns are eigenvectors. So remember to say that this orthogonally diagonalizes the matrix A. How do we remember which order it is? Does A equal P times D times P inverse, or is the other P and the P inverse the other way around? Well, this is how I always remember it. I'll just make a note down here. I mean, we went over this yesterday, but remember the definition of eigenvalue and eigenvector is just summarized in this matrix equation, AP equals PD. So if you can always remember AP equals PD, if you can remember that equation, then you should be able to remember the order of the inverses. Okay, so that means in this case that A is equal to P times D times P inverse, but P inverse is equal to P transpose. All right. So we've formed this orthogonal matrix P. Can anyone tell me what the matrix D looks like? Okay, I mean, there's one important point to note when you diagonalize a matrix. Okay, if you take the eigenvectors, if you take the eigenvectors of the matrix, put them into the columns of P, what was one of the points I was making in yesterday's lecture? Is that the order in which the eigenvalues appear down the diagonal must correspond to the order in which those eigenvectors appear. And that just comes from the fact that AP equals PD is just summarizing the definition of eigenvalue and eigenvector in each of the columns of this matrix equation. All right, so I've stated at the top of the page here that we know the eigenvalues are -3, -1, and -4 with corresponding eigenvectors V1 and V2, or V1, V2, and V3. By that, we mean that V1 is the eigenvector corresponding to eigenvalue -3, V2 corresponds to -1, and V3 corresponds to -4. I'm pretty sure that's what we found yesterday. So in that case, if I've placed V1, or at least V1 hat, which is just a scalar multiple of V1 into the first column, that means for D, the corresponding eigenvalue must appear in the first column. The second column of P, we've got an eigenvector corresponding to eigenvalue -1. And in the third column, we've got an eigenvector corresponding to eigenvalue -4. All right, so just remember there is a little bit of freedom we have for choosing the order. In fact, we can choose any order in which these eigenvectors appear, but the important thing is whatever order we choose for those eigenvectors to occur in the matrix, in the columns of the matrix P, we must choose the corresponding order of the eigenvalues on this diagonal D. Okay, guys, well, that's orthogonal diagonalization. I might just take a little break, and we'll look at the next chapter after the break, which actually is an application of orthogonal diagonalization. Just before I get into the details of this lecture on quadratic forms, just recall right back, remember our first lecture, back to chapter 1 of the workbook, page 15 it was. I can't remember exactly what the differential equation was, but it was, we end up finding a solution to this differential equation. We end up giving the equation, giving the solution in this form, xy equals a half x squared plus some constant as the general solution. And I think I made the comment that this is a family of hyperbolas. I may have even shown a few graphs. I may have even taken to MATLAB with that one and shown you a few graphs of a few families of the solution curves to demonstrate exactly what I meant by a family of hyperbolas. But I also made the comment that we'll understand this in more detail when we get to chapter 34, and that's where we're at now in this this lecture on quadratic forms. In fact, I guess this is one of the big applications of the orthogonal diagonalization. It's one of the applications of orthogonal diagonalization anyway, is to classify all the conic sections So these conic sections, you'll find some discussion in Stewart on page 694. There's a section on conic sections. There's a chapter or a few pages discussing conic sections in Stewart. What they are, I mean, I should have brought some diagrams along to show you, but what they are essentially is where you take a double cone in 3 dimensions, so something like this, and you work out the intersection, or you work out what the curve looks like that's the intersection of this double cone and a plane. So as a plane comes down and intersects this surface, it turns out you get several different classes of curves which are called conic sections. So these are the parabolas, hyperbolas, ellipses, which include circles. So you can see well, maybe you can imagine, it's difficult to see from this terrible little diagram I've got here on the page. If you've got a double cone and intersect a plane with that cone, imagine placing the plane parallel to the edge of the cone. What sort of curve will you get then? Well, actually it'll be a parabola. What happens if you rotate the cone so that it intersects both parts of the double cone? Well, they're the hyperbolas, right? What happens if you rotate the cone so it's either flat, you could get a circle, or if you rotate it slightly so it still only passes through one cone, it could be an ellipse, right? As you rotate it more, the ellipse becomes elongated till it becomes a parabola, and then when you rotate the plane more, you're back to the hyperbola. I mean, you can also see you get really boring ones. If I place this plane right along the edge, right on the edge of the cone, I'll just get a straight line. So that's what we call a degenerate conic section. I could even be I could even arrange it so that the plane passes through that single point, right? That's another example of a degenerate conic section, just a point in the plane, right? Not particularly interesting. What we're going to look at, though, is a way of classifying the non-degenerate conic sections, so all the parabolas, hyperbolas, and ellipses, which include circles. Right, we're going to have a look at classifying them and I guess understanding them using orthogonal diagonalization, what we've just looked at before. Okay, so first what we need to do, though, is understand quadratic forms, right, and understand what we can do with quadratic forms and actually how we can write them in a matrix representation. And this is really where the results on orthogonal diagonalization will come into play. All right, so firstly, just to define a quadratic form, is if we have any number of real variables, so here I've listed n real variables, x1, x2, up to xn, then a function of this form, where it's just a linear combination of all possible quadratic terms, so all possible products of xi with xj, so all paired up, so these are only ever quadratic terms. This is called a quadratic form. And these coefficients, these aij's, are just real numbers. All right, so if we've got 2 variables, the most general quadratic form that we can write down is of this form. So it's a linear combination of x squared, y squared, and xy. This is what we call a cross term often. Okay, so x squared, y squared, and xy are only the 3 possible quadratic terms that you can get from 2 variables. What if we have 3 variables? Well, we end up with 6. So if we have the 3 variables x, y, and z, so we get the 3 squared terms, right? So ax squared plus by squared plus cz squared, and then we get these 3 cross terms. So the xy, the xz, and the yz. All right, now, here's the first observation. It turns out what we can do with a quadratic form is we can always express it as a matrix product. We can always express it in this way, V transpose times a matrix A times V, where V is just a column vector with the n variables. So if V is the column vector, V transpose is the row vector, and A is a symmetric matrix. So we can always do that. Right? So for example, this quadratic form in 2 variables that I've written here with 3 terms, I can actually write that as this matrix product, okay, with a 2 by 2 matrix here. So so this vector V is the vector of the variables, so with entries X and Y. Okay, now this matrix I've chosen the numbers so that it's a symmetric matrix. So we could actually choose, any numbers in these off-diagonal entries of the 2 by 2 matrix, as long as they add to give the coefficient C. So it turns out the entries on the diagonal, so in the first entry on the diagonal will always be the coefficient corresponding to the first variable squared in this vector V. All right, so the A here is the coefficient of x squared, and x is the first variable I've placed in this vector. The other entry, it's only a 2 by 2 matrix we've got here, so the other entry on the diagonal is B, is actually the coefficient of the y squared. And so you can see when you multiply out this product, right, you can see where all these terms come from. Okay, so I mean that might be an exercise. Just try one step at a time, try multiplying out this this matrix product, right? It doesn't matter what order you do it in. The matrix algebra is associative. So you multiply up these last two and then multiply that with this row vector xy, and you find you indeed get this quadratic form. I mean, this is a 1 by 2 matrix. Think that's a 2 by 2 and think of that as a 2 by 1. So the whole thing just evaluates to a number, or in other words, a 1 by 1 matrix. Right, so these off-diagonal terms will contribute to the cross term, the xy, will contribute towards the coefficient of the product xy. But I've chosen these numbers here so that they're the same. So in other words, I've got a symmetric matrix. And what do we know about symmetric matrices now? We know they're orthogonally diagonalizable. Okay, it's what we've just finished looking at. There's this correspondence, okay, there's this equivalence between symmetric matrices and all the orthogonally diagonalizable ones. Alright, so what that means is we know we can diagonalize this matrix. So, what if it was a diagonal matrix in here? If it was a diagonal matrix, C would have to be 0. And if C was 0, it would mean I have no cross term. Right? It would mean I only have a linear combination of square terms. That's just something, an observation I want to make just at the start. We'll come back to that later on. All right, so that was for just an example of the 2-variable quadratic form. What about the 3-variable quadratic form? So with these coefficients, I've got it on page 214 here. We've got 6 terms. So now we're dealing with 3 variables. So I place those variables into a column vector, x, y, z. So this is the V so that's the vector V, column vector V. This is V transpose, that row vector. And this 3 by 3 matrix is the matrix of coefficients. But note, these entries have been chosen so that it's a symmetric matrix. So again, regarding the diagonal entries, notice the entries A, B, and C are just the coefficients of the square terms, right? The x squared, y squared, and z squared term, in that order, right? And so the order in which they appear on the diagonal correspond to the order in which I've placed these variables into the column vector here. All right? What about the off-diagonal terms? Well, I mean, you can see those two. If we multiply out this matrix, so when we take this product of the matrix by the column vector, that D on 2, that entry D on 2 is going to hit the entry Y, and then when we multiply that column vector will have a d on 2y at the top, will hit the x in the first entry of that row vector. So actually those two guys will contribute to the xy term in the quadratic form. I mean, try multiplying it out. That's something maybe you guys should do as an exercise. Multiply this product out if you don't believe me. Right? These terms will contribute, these off-diagonal terms, the e on 2, will contribute to the xz term. And you can see that if you multiply out the matrix product. All right, so these two guys contribute to the xz term. And finally, these two terms, the f on 2, will contribute to the yz term. Right? This is something you can see just by direct multiplication. But the thing is, I've chosen those entries on the off diagonal by taking the coefficient of those cross terms and just dividing them by 2, splitting it up equally and placing them into those entries. All right, so I guess the message is we can always do this with a quadratic form in any number of variables. All right, if we've got a linear combination of quadratic terms, we can always express it in this way. So that's the first observation, I guess. So here's just a little exercise, is give the matrix representation of this quadratic form in 2 variables. So what we want to do is write this. So the 2 variables are x and y. So I want to write this. So this is what I mean by the matrix representation. I just mean write that as a matrix product, and so that this matrix is a symmetric matrix. So when I say give the matrix, right, not give a matrix representation, give the matrix representation, it's unique, right? It's a unique symmetric form. So that matrix is a symmetric matrix. All right, so let's just start with the diagonal entries, right? So x is the first variable. So the coefficient of the x squared is 2. So that's got to be the first entry, or the first entry in the diagonal. The coefficient of y squared is -7. So the -7 is going to go in the second entry on the diagonal. These off-diagonal entries will just contribute to the cross term, whose coefficient is 6. So if I take that coefficient and divide by 2 and place those numbers into the off-diagonal entry, that's going to be the unique symmetric matrix that gives the quadratic form. Okay, so just to make that clear, maybe, I mean, for 2 by 2 matrices, it's not so difficult to answer the question of diagonalization, because you can only ever have, at most, 2 linearly independent eigenvectors, right? In the case we only have one eigenvector, then we can't diagonalize. Right, so we could also use this quadratic form. So we still have to have 2 and -7 in those entries. But what if I chose, say, 4 here and 2 there? Well, when I expand this, I'll still get the same quadratic form, right? I'll still get the same. I'll still get 2x squared plus 6xy minus 7y squared. But the question is, can I diagonalize this matrix? So this is what I mean. For a 2 by 2 matrix, it's not a difficult question to answer. Right. Just as an aside, work out the eigenvectors of that matrix. what are the eigenvectors of this matrix? Just a little question for you to work out. So look, this is the point, right? So we could also use this matrix, but the question is, can we diagonalize it? Well, in general, I mean, for a 2 by 2 case, it's not so difficult to answer. If we had 10 variables, well, then it might be difficult to answer that question easily. But if I made it a symmetric matrix, then I could answer it straight away. If it's a symmetric matrix, then I know I can diagonalize it. And in fact, I know I can orthogonally diagonalize it. Right? So that's the point. We want a symmetric matrix in here. We want a symmetric matrix so that we know we can always diagonalize a symmetric matrix. Okay, so we now know about matrix representations of quadratic forms. We know about diagonalization. So let's